Welcome back. Today we will going to discuss about the solved examples of the resonance circuit. The problem statement is that a pure inductance of 150 millihenry is connected in parallel with the 40 microfarad and capacitor across a 50 volt. Here we find the problem. A pure inductance of 150 millihenry is connected in parallel with 40 microfarad and capacitor crosses the 50 volt and the variable frequency supply. And to determine the parameters, there is a first we have find out the resonant frequency of the circuit. Second is the current circulating in the capacitor and inductance at a resonance. From that circuit diagram, there is inductor value L which is equal to 150 millihenry, C which is equal to 40 microfarad, and inductor and capacitor both are connected in parallel, and the voltage drop across 50 volt is the voltage drop across the capacitor and inductor respectively. So first we find out the resonant frequency. We must know that to find out the resonant frequency, with reference to the circuit diagram, the value of L which is equal to 150 millihenry and C which is equal to 40 microfarad. Therefore resonant frequency which is equal to 1 upon 2 pi square root of LC. Therefore here the resonant frequency which is equal to 1 upon 2 pi square root of LC. Therefore its value is 1 upon 2 pi square root of 1 into 150 millihenry. 150 millihenry, 1 upon 2 pi square root of LC means 150 into 10 raised to minus 3, and 40 microfarad is 40 into 10 raised to minus 6. That's why 1 upon 2 pi, here is a 150 into 10 raised to minus 3, and here is a 10 raised to means minus 9, and minus 9 there is a 10 raised to 2, therefore there is a minus 7. That's why here is the 1 upon 2 pi, 15 into 4 is the 60 into 10 raised to 7, therefore here is a 10 raised to 3, 10 raised to 3 into 2 pi upon 1 upon 6 means this value we have to be calculated 64.97 hertz. Means the value of the resonant frequency is the value of the resonant frequency, and that value of the resonant frequency f of r which is equal to here there is a 64.97 means this value is 64 point, here is the 64.97 means the value is a 64.97 hertz. This is the value of the resonant frequency. Then we have moved towards the current circulating in the inductor L and C at a resonance. There is a V upon Xc means for voltage upon the capacitance. Therefore V upon 1 upon 2 pi square root of LC. Therefore its value should be given 1 upon 2 pi FRC into V, and this value should be given 2 pi. Here operating frequency is 64.97 into R value 40 into 10 raised to minus 6 into 50 ohm. Means this value should be given 0.816 ampere. So alternating current should be given V upon XL, and that V upon XL should be provided. There is a 50 upon 2 pi, resonant frequency is 64.9, and here is the 150 millihenry means 0.15 henry. Therefore its values alternative current should be 0.817 ampere. So in the next example, in case of the next example, the problem statement about it, the problem statement is a series RLC circuit has a sinusoidal input voltage of the maximum value is the 12 volt, and if the inductance L which is equal to 20 millihenry means this value is given. See here, this value is basically the voltage which is to be given 12 volt. This is the applied voltage. Then if the inductance value L, which is equal to 20 millihenry, means this value is given 20 millihenry. The resistance value 80, which is equal to R, which is equal to 80 ohm. The capacitance value is given C, which is equal to 400 nanofarad. Means there are 4 parameters should be given. One is the voltage is given, second is the inductor value is given, third is the resistance value is given to you, and fourth is the capacitor value is also given. So the maximum whatever the required data, that will be already given in the problem statement. So you have to find out the resonant frequency. First parameter you find out the resonant frequency. Second parameter you find out the potential difference across the capacitor at a resonance frequency, and third is the frequency at which the potential difference across the capacitor is maximum, means you find out the frequency, operating frequency. And next is the value of the maximum voltage across the capacitor, that parameter is asked here. So the resonant frequency is calculated Fr, which is equal to 1 upon 2 pi square root of Lc, which is equal to 1 upon 2 pi square root L, which is equal to 20 millihenry. Therefore L, which is equal to 20 into 10 raised to minus 3. Then C is the 400 nanofarad. Here is the 400 nanofarad. That's why its value is 400 into 10 raised to minus 9. Means here operating frequency, once we calculated its resonant frequency should be given 1779.4 Hertz. This value will be given for the resonant frequency. Then second is the Vc, which is equal to Q into V. Q is stands for the quality factor, and quality factor which is equal to XL upon R, means reactance upon resistance, that will be given by the quality factor. Hence the Q, which is equal to omega R, which is equal to 2 pi Fr, means this value should be given. There is a 2 pi resonant frequency F of R and 2 pi Fr, means this value will be substituted here. Means this value is, there is 2 pi Fr is 2 pi, and your operating frequency is 1779.4 into L. L value should be given 20 millihenry. That's why here is the 20 into 10 raised to minus 3 upon 80 ohm. Means once we find out the quality factor Q, which is equal to 2.80, means finally to calculate the value Q, which is equal to 2.80. Therefore Vc, which is equal to Q into V, the voltage drop across the capacitor, which is equal to quality factor into the applied voltage. That's why 2.80 into 12, which is equal to 33.60 volt. This is the voltage drop across the capacitor. The next parameter is find out from this the resonant frequency F at which the Vc is a maximum. That's why F, which is equal to Fr into under root of 1 minus 1 upon 2q square. Your operating frequency is given 1779.4 into under root of this value, root of 1 minus 1 upon 2q square, quality factor Q, which is equal to 2.80. Here is given 2.80, means here the quality factor Q, which is equal to 2.80. That's why here is able to substitute. Then 2 into 2.80 square, which is equal to 1721.7 Hertz. This is the frequency at which the Vc is a maximum. Then last is that to find out the voltage drop across the capacitor when the maximum value of the voltage, means the maximum value of the potential difference across the capacitor is given, which is equal to Qv upon root of 1 minus 1 upon 2q square. Means in the previous example what asked, the frequency at which the Vc is a maximum, and here is to ask the value of the maximum voltage drop across the capacitor, means the maximum value of the voltage drop across the capacitor, which is equal to QV upon root of 1 minus inside the bracket 1 upon 2 Q square, which is equal to, the quality factor is 2.80, the voltage drop across the voltage is 12, then second is 1 upon 2 into 2.80 bracket raised to square, which is equal to 34.15 volt. Means the voltage drop across the capacitor when input voltage here to calculate it, the value of the maximum voltage of the capacitor. So we find out here the maximum voltage drop across the capacitor is 34.15 volt. So next example. In this example, a coil of the inductance, means the value of the inductor should be given L, which is equal to 5 millihenry. The resistance value should be provided R, which is equal to 10 ohm, and connected in parallel with 250 nanofarad, means the value of the capacitor, and the value of the capacitor should be provided C, which is equal to the 250 nanofarad. The voltage drop across the capacitor is the 50 volt, the variable frequency supply. So find out here the resonant frequency FR. Second parameter is the dynamic resistance. Third is the current at a resonance, and fourth is the circuit, the Q factor at a resonance. So the resonance frequency we calculated FR, which is equal to 1 upon 2 pi root of 1 upon LC minus R square upon L square. So here 1 upon 2 pi under root 1 upon LC, the value of L should be provided 5 into 10 raised to minus 3. The value of the inductor is provided 5 millihenry, into C, capacitor should be provided 250 nanofarad, therefore 250 into 10 raised to minus 9, minus R is the 10 ohm, R square means 10 square upon 5 into 10 raised to minus 3 bracket raised to square, which is equal to 1 upon 2 pi root of 800 into 10 raised to 6 minus 4 into 10 raised to 6. Therefore 800 minus 4 means 796 into 10 raised to 6, which is equal to 4490 hertz. Means whatever the operating frequency we have calculated, that operating frequency FR, which is equal to 4490 hertz. Then from that equation, the dynamic resistance we calculated, the dynamic resistance RD, which is equal to L upon CR, which is equal to, the value of the inductor is given 5 into 10 raised to minus 3 upon 250 into 10 raised to minus 9 into 10, means the dynamic resistance R of D, which is equal to 2000 ohm, means basically this answer is a 2000, means here 2 kilo ohm is the dynamic resistance. 2 kilo ohm. So next is the current at a resonance. The current at a resonance, we calculated the value of I of R, which is equal to V upon RD, V upon R of D. The voltage drop across the capacitor should be provided. There is a 50 volt, here is the 50 volt, this 50 volt is provided, that 50 volt will be taken here, and the dynamic resistance is the 2 kilo ohm. Here is the dynamic resistance is the 2 kilo ohm. Therefore this 2000 ohm means 50 upon 2000, which is equal to 25 milliampere. Means current at a resonance, means where XL, which is equal to XC, the current at a resonance is the 25 millihenry. Then Q factor at a resonance, there is a reactance upon inductance upon the resistance. Therefore the quality factor QR, which is equal to XL upon R. XL means omega R L upon R, means 2 pi F R into L upon R. This value is 2 pi L. L value should be given 2 pi F R. Its value is 4490 into 5 into 10 raised to minus 3 upon 10, means the quality factor Q, which is equal to 14.1. Means in this way we have calculated the different parameters regarding the resonant circuit. It may be connected in the series as well as in the parallel motion. So here once again we have to be compare the series resonance and parallel resonance in the form of the frequencies. First is the circuit, where in case of the circuit in series resonance, the resistance R, capacitor C and inductor R, it will be connected in, or it will be L also connected. Therefore R, L and C will be connected in series fashion. Here is the current source. Basically here you use the current source, across it the parallel resistance R, L and C connected in a parallel. Then its transfer function should be given. The second parameter is the transfer function. In case of the transfer function, the h of omega, which is equal to omega RC upon 1 minus omega square LC bracket raised to square plus omega RC square. And in case of the parallel resonance, just we have changed here omega L. Therefore h of omega, which is equal to, here is the ratio to take the voltage drop across the resistance to the voltage drop across the inductor or total source, that will be find out. And here is the voltage drop across the resistor to the main current source, means we take the ratio. Here is the transfer function. Then the resonant frequency. In case of the resonant frequency, the omega 0, which is equal to 1 upon root of LC. Here is also omega 0, which is equal to 1 upon root of LC. Then half power frequency should be given. In case of the half power frequency, here the half power frequency, there are the two frequency. One is the lower cutoff frequency and upper cutoff frequency. Its value should be same, just to change the sign, minus R upon 2L plus root of R upon 2L bracket raised to square plus 1 upon omega 0 square. And omega 2, which is equal to R upon 2L plus root of R upon 2L bracket raised to square plus 1 upon omega 0 square. Means this is the half power frequency regarding for the series RLC circuit. In case of the parallel RLC circuit, the equation should be same. Again here the lower cutoff frequency, here is the lower cutoff frequency omega 1, which is equal to minus 1 upon 2 RC plus square root of 1 upon 2 RC square plus 1 upon omega 0 square. And omega 2 is the upper cutoff frequency, is the 1 upon 2 RC plus square root of 1 upon 2 RC square plus 1 upon omega 0 square. This again we have compared here series and parallel circuit with reference to the circuit diagram, transfer function, resonant frequency and the half power frequency. Then next is the bandwidth. The bandwidth should be given. In case of the series resistance, there is a beta which is equal to omega 2 minus omega 1, which is equal to R upon L. And in case of the parallel resonance, the bandwidth which is equal to omega 2 minus omega 1, which is equal to 1 upon RC. Then the next parameter is the quality factor. In case of the quality factor Q, which is equal to omega 0 upon bandwidth omega 0 L upon R, and which is equal to 1 upon omega 0 RC. This quality factor in concern with the series resonance circuit. And in case of the parallel resonance circuit, the quality factor Q, which is equal to omega 0 R into omega 0 upon bandwidth omega 0 RC, which is equal to R upon omega 0 L. This is the bandwidth regarding for the parallel resonance circuit. So I hope that would you enjoying the solved numerical problem based upon the parallel resonance circuit and series resonance circuit. Thanks for watching. Please subscribe my channel and click on the bell icon. Thank you very much. Have a nice day.